Everyone. Shall I start?
Yes, please.
Okay. I'm a second year student. I work with Dr. Mamoras. Today I'm going to talk about a formally verified monitor. So often we expect cyber-physical systems to satisfy certain properties. For example, an aircraft carrier might be interested in maintaining that the aircraft never reaches high velocities in low altitudes. An online monitor is a system which interprets such behavioral information in real time and produces judgments. For example, given this graph on the left, an online monitor would look at it and incrementally produce judgments to say whether there are any problems, as indicated by the red bars on the right. Since these kind of online monitors can be mission critical, it is very important that we have confidence in their correctness. As anybody who has written a program ever knows that having confidence in the correctness of software is a very difficult job. Indeed, monitors have been studied for a long time, but what we really want to do here is establish that a monitor is as correct as possible. To move forward, the way we propose to do this is to use proof assistants or interactive theorem provers. An interactive theorem prover is an environment where after implementing a program, we can state correctness properties in terms of mathematical theorems, and then we provide rigorous proofs, which will then be checked by the assistant. Human check proofs often rely upon a vast amount of background knowledge and intuition that the human reader has. However, this sort of knowledge is missing with the proof assistant, and this is what makes verifying algorithms with proof assistants a difficult job. We have formalized a monitor for a class of temporal properties using the proof assistant COC. In this talk, we are going to talk about some aspects of our formalization. Let us start by looking at linear temporal logic, which forms the basis for our formalization. The building blocks in linear temporal logic are the atomic proposition. To continue with the airplane example, this might correspond to some events like the altitude being too low or the velocity being too high or some engine being on. And then the formulas which are the specifications we have correspond to are interpreted over some kind of traces which are finite valuations of these atomic propositions. The atomic propositions are the simplest formulas here are the atomic propositions. They are interpreted over the traces, and for example, we say that the trace W satisfies P because in the latest event of W, P is true. Similarly, we also say that W satisfies Q. We have Boolean connectives like and or, which are interpreted in an usual way. Here we say that S always holds. This means that in every valuation of the trace, S is true. Similarly, we say sometime R, indicating that at least in one valuation of the trace, R was true. Sometimes we wish to annotate our temporal operators with intervals like this. Here we say sometime 0,3R to indicate that the event R which we care about must have occurred within 0 to 3 units ago. Instead of looking at valuations of propositions in a Boolean way, we might want to directly look at signals which have numerical values. In this case, instead of atomic propositions, we would like to look at predicates which compare the components of the signal directly with constants. Linear temporal logic classifies traces as correct or incorrect. However, there might be behaviors which might be more desirable than others. For instance, given a trace which satisfies the specification, we might want to ask the question, how much perturbation is acceptable to the trace? And indeed, if a trace is resistant to more perturbation, it would be more desirable than others. This is what it motivates the need for a quantitative semantics for our logic. One way to approximate this problem is to replace the role of conjunction by infimum and disjunction by supremum. Motivated by this idea, let us look at this trace W and look at how some simple formulas can be interpreted with it. So consider the formula A greater than equal to 10. With this formula, we assign the value 5, indeed plus 5. The positive sign here denotes that the formula is indeed satisfied. And by 5, what we mean is that changing the trace anywhere by at most 5 units would not change the status of satisfaction. It would still continue to be satisfied. On the other hand, to the formula b greater than equal to 40, we assign the value minus 10. Indeed, b is not greater than equal to 40, and this is why we have the negative sign. And perturbing the formula, the trace anywhere by at most 10 units would not change this. Consider the disjunction of these two formulas. To interpret this, we take the maximum of the two corresponding values. By the way, I sometimes will refer to this quantity as the robustness. So to interpret this robustness of the disjunction, we consider the robustness of the maximum value of the robustness of these two formulas. This is plus 5, and indeed this disjunction is satisfied, and again changing this anywhere would not, by at most 5 units, would still allow the trace to be satisfied. We have now looked at two different kinds of semantics for temporal logic. Let us compare their main features. In propositional LTL, the traces were sequences of d tuples of booleans. Each of them were components which indicated some atomic propositions. On the other hand, in quantitative STL, we have tuples of real numbers denoting components of some signal. In propositional LTL, the formulas were interpreted as true or false. On the other hand, here we had reinterpreted this with real numbers, and or were interpreted using mean and max respectively. The building blocks in propositional LTL were the atomic propositions. On the other hand, we had atomic predicates here, which were the comparison operators. In the general setting in which we have formalized our algorithms, we consider traces which come from any arbitrary domain, and the truth values we have are required to be a bounded distributive lattice. A lattice is simply an ordered set where the infimums are well defined. We call them meet, and so are the supremums, which we call join. We require the lattice to have a greatest element top and the smallest element bottom. And we further want this meet and join operations to distribute over each other. We require a class of functions, which we call the atomic predicates, from this domain to the lattice of truth values. In this setting, we can give a definition for an interpretation for the temporal logic formulas we have. However, we are not interested in the static definition, but computing these robustness values in an online fashion. Given a trace to an online monitor, it would give us corresponding robustness values at every step. To formalize this notion and prove its correctness, we need a mathematical way to model this kind of algorithms. We propose to do this via the use of Moore machines. Moore machines are simply stateful machines which have an output, which we write here as mout, associated with every state. And the state of this machine can be updated via the function mNext, which consumes a token of input and updates the state. In our formalization, we use a co-inductive definition in which the state is not made explicit. Instead, the machine is identified with its output and how it evolves. Consider some monitor M, which implements a monitor for the formula phi, and a monitor for the formula, and a monitor N for the formula psi. Now we could combine them in the following way. We could consider a monitor which internally keeps a copy of M and N, and given new inputs, it steps them forward by feeding both of them the same input, and as for its output, it computes their meet. Now this construction would give us a monitor which would compute the robustness value for phi and psi. This kind of construction for which compose monitors in a certain way is what we call combinators. We have already seen the combinators for AND and OR. In a similar way, we propose to solve the problem of constructing a monitor by figuring out a combinator for every logical connective. As a base case, we would have the atomic predicates, and to monitor them, we need to simply compute the function at the latest input. We have implemented combinators, one for each logical connective. Some of them, like that for those for sometime and always, require maintaining buffers. The space consumed by these buffers is proportional to the constants that appear in the formula. This space consumption is unavoidable. However, the time overhead that each of them introduce is O of 1 and is independent of the formulas that appear in the constants that appear in the formula. To construct the monitor, we simply need to recurse through the structure of the formula and replace each connective by the corresponding combinator. And to prove this, we need to prove the correctness of this entire process, we need to show that each of these pieces individually is correct. The way we have organized our proofs is in a compositional fashion. This means that to prove the main result, we prove smaller pieces. For example, to prove the correctness of the construction of the AND combinator, we need a theorem that says something like this. If there is a monitor M which implements a formula phi and a monitor N which implements psi, then the corresponding construction would implement a monitor for phi and psi. To prove these, we need to pass by invariants about the final result and the final state. This is what we get from the monitor after feeding it a trace of arbitrary length. And we prove each of these results via induction. Although our primary goal here was to obtain a monitor which is formally proven correct, as an added bonus, the performance of the tool that we produced is reasonably well. Here we extracted our coq proof scripts into OCaml code and ran some experiments on them. Here we see that the throughput of our monitor is reasonably good and its performance does not deteriorate very much with increasing the constants. In summary, we gave a generalized quantitative semantics for metric temporal logic using lattices, and we modeled the online monitors as Moore machines. And we constructed monitors for arbitrary formulas using the idea of Moore combinators. We have verified our construction in coq. We extracted this into OCaml code and saw that it performs reasonably well. Thank you for listening. I'm happy to take any questions. Oh, we have a question in the chat. If the constraints for some variable are very complex, will this lead to a very long and complex Moore machine? Will this affect the throughput? Yes. So imagine that a formula is fundamentally made up of connectives. Like let me look at this example. So here, for example, we have this formula which was made with two connectives, say one always and one odd. So what I have done is I have used one combinator for each of them. So each of these combinators introduce some overhead, but this overhead is reasonably small. So the time overhead from each of these combinators that we would get is O of 1. And but yeah, indeed you are correct. Like if we consider reasonably large and large formulas, then the monitors would become complex and complex, and it would become it would affect the throughput. But usually when you in an application, you would imagine a fixed formula with a certain number of combinators, and the formula itself is not very large. Can this be extended to data flow combinators? Yes, I want to uh, phrase my proofs later in that fashion. In fact, that would be more compositional than it is right now, and I think that would be a good scope for future work. Thanks. So do we have any more questions? So as I pointed out in the beginning, perhaps I did not spend very much time on this. There are some cases in which you have formulas which have annotations on them. So here you have these formulas which, for example, like just look at this Boolean case. This knowing this sometimes 0,3 of R would require you to remember what happened the last three moments. And indeed, there is no way around this. So this is why we need the OK space. The K is the 3 that appears here. Thanks. Okay, I believe there are no more questions. Thank you, everyone, once again.
Let's go ahead and thank today's speakers. I'm not sure if the applause